Hello there. Let's start a new topic: magnetism and electromagnetism. Uh, first thing is magnets. Magnets are some kind of material that attract iron-containing objects. And something that we should know is like magnets have two distinct poles. So always, like any piece of magnet that you may encounter, it has North Pole and South Pole, and those names are derived from the magnetic behavior of the Earth. Okay, so what we know, like charges, from our previous discussion, like charges repel each other, and like charges attract each other, right? Then, like charges, magnets also experience like some kind of attraction between them and repulsion between them. So like poles of magnets, if you take two pieces of magnets and then you bring them together or close to each other, then they repel each other if their like poles are close to each other. On the other hand, if you bring the south pole against the north pole of another magnet, then they will attract each other. Okay. So like electric field, there is also something we call it magnetic field. So if you try to connect like the dots, we have seen gravitational field, or this gravitational field in Woodman, our main focus in one of the previous chapters that we saw. Electric field, we saw that like positive charges have an outwardly going electric field, and negatively charged particles or objects have an electric field like that moves inward. Likewise, magnets have their own field, and in general its field runs from its north pole to its south pole, as the way you see it here in this diagram. If you take small compasses and if you put them around a magnet, what will happen is like they're going to align themselves like this is the north, right? So this is the north pole of this compass, this is the north pole of this compass. In general, the direction of the magnetic field will run from north to south pole. So if you put, like, for instance, if you don't know the south and the north pole of a small piece of magnet, if you come across it, but if you take a few magnetic compasses, and around that piece of magnet, what will happen is like the compasses will arrange, if the compasses will arrange themselves in such a way that like the direction of the magnetic field runs. Okay, all right. So magnetic field, Earth's magnetic field, it is very similar to just a small magnet. You can imagine like the Earth has one gigantic piece of magnet inside it, okay, running from its north pole to its south pole. So something that we should know is like, for instance, if you take the Earth, let me take you back. If you take the Earth, like as one big object like this, okay, I'll show you like what we know is like this is the North Pole and this is the South Pole of the Earth, right? But that's in our day-to-day conversation. And this north and this south, those are known as geographic poles. Those are not magnetic poles. So poles, geographic. Okay. And the South Pole, and use a different color probably, so that like so this South Pole is here, North Pole is here. That is the magnetic pole of the Earth. Okay, so the magnetic pole of the Earth is different from the geographic pole. Okay, So the magnetic pole, south magnetic pole of the Earth is nearer to the north geographic pole, and likewise the north magnetic pole of the Earth is something closer to the geographic south pole. So we already talked about like magnetic field. So if you have a magnetic field, if you have a magnet, its magnetic field runs from north to south. And if you have like two charges close to each other, their magnetic field normally runs from the positive to the negative charge. Okay, so we represented electric field and we did examples. Please watch the previous video and you will see E as the electric field representation. On the other hand, magnetic field is represented by uppercase B. Okay, pretty much throughout the material. So as we already said it, like the direction of the field runs from positive to negative for electric field, whereas for magnets it runs from the north pole to the south pole. So there's a magnetic field between two magnets, right? So if you have two bar magnets, you have north pole and south pole, and the force is attractive between them. Okay, and if you have like similar north to north close to each other, then the force is going to be repulsion. Okay, so you may wonder like about the strength of this magnetic force. It's mostly beyond the scope of this material, but if you remember like the electrostatic force between two charges, right, was like K times Q1 times Q2 divided by R squared, right? So yes, you have then this, and this is electrostatic force, or just let's say the Coulomb's force. Okay, this Coulomb, the same Coulomb scientist, he also observed like a similar kind of force between magnets as well. Like this is electrostatic Coulombs, okay, between two charges. But fascinatingly, like that same person, that same scientist, observed the same kind of or similar kind of ideology that like forces between magnets is the inverse is proportional to the inverse square of distance between inverse distance square. So this is the magnetic force. Okay, so the magnetic force, that same Coulomb that developed the electrostatic force, he also experimentally observed that magnetic force is proportional to the inverse distance square between the magnets. Okay, so in a little advanced class, then we'll definitely use a similar kind of equation to solve the magnetic strength of force. But for now, it's pretty much enough to understand like the forces experimentally were observed to change proportional to the inverse distance square between the magnets. Okay. It's similar to what happens in electrostatics. If you remember, like if you have two charges close to each other, and if you have like two charges that same charges, like if you take them apart twice a distance, then the force between them decreases by a fourth, right? So we saw those ones, right? So now if you consider like the Earth's magnetic field, how does it run? So as mentioned earlier, like if you consider the Earth has like a huge, gigantic magnet in its, in its inner core, because of all the minerals and things that it has inside. So then it has a very nice magnetic property. That magnetic property has its own, impact in our day-to-day life, and of course it has a lot of benefits, like in terms of diverting cosmic rays. Okay, as mentioned earlier, the magnetic south pole of the Earth is up here, and its geographic south pole is down here, whereas the magnetic north pole is indicated. So therefore, the magnetic field of the Earth normally just runs from its north pole to the south pole. That means like the direction of the magnetic of the Earth runs like this. Okay, from the southern hemisphere to the northern hemisphere. Okay. Now let's go ahead and then consider electromagnetism, a little bit of electromagnetism here. So magnets and then the effect of current. Let's just start with that. So for instance, like if you get like if you get like a charge, let's say, or a charge carrying wire, it means moving charge, let's assume. So if you have like a current carrying wire, if you consider this one for now, like we may ignore this one. So what would happen is, like, by virtue of having current flowing through this wire, the wire has a magnetic field. It develops a magnetic field. So you may consider like, oh, so how in the direction of the magnetic field, it depends on like how the current is flowing in that one. So for instance, here if you read it, like here it says a long straight current carrying wire has a cylindrical magnet. So that means if you have a wire and if current is flowing through it, so that means that wire acts as a magnet itself, and it has like some magnetic field around. So therefore its magnetic field is in a cylindrical shape. That means like, it just runs around the wire. So if this is the wire, like as you can see it here, so if this is the wire, so therefore its magnetic field is going to move in that direction. So on the other hand, if you have the wire is moving, or I mean the current in the wire is moving downwards, so the way you see it in the second one. So if current is moving in the downward direction, then its magnetic field is going to be in the other direction. Okay, see, like that. So you may wonder that, like, if there's any kind of general consensus to find this magnetic field in a current carrying wire. And of course there is a general convention known as like the right hand rule. Okay, so what the right hand rule says is like, so align your thumb in the direction of the current, then curl your fingers, and the way your fingers are curling indicates the direction of the magnetic field. It's a very basic kind of right hand rule. Again, just keep in mind the only thing that you have to use here is just your right. So that means like your thumb, if you indicate your thumb in the direction of the current carrying wire, or in the direction of the current, then automatically the way your fingers curl themselves, your fingers only curl in one direction, right? That's it. They curl towards your palm, not the other way around. So that direction, as you can see it here, right, drawn, then that is what the direction of the magnetic field is. Okay, so in a current carrying wire, then that's how you will normally be able to find the magnetic field. So if you have a current and if you have a magnetic field, then that means like there is an interaction between the current and the magnetic field itself. So therefore there has to be a certain kind of like magnetic field that would be developed in for this wiring. Okay, so if you have two current carrying wires, so we're saying that like we already mentioned this before. If you have two magnets, like two bar magnets, like if you bring them close to each other, right, then they will experience some kind of force between them. All right, so this, in this particular case, you know, they'll repel each other. The forces, just this one pushes and that one pushes, you know, in the opposite direction, this direction, right? So now it's repulsion kind of force between the two. Okay, now if you bring two magnets, they either repel or not repel each other, because this one of the magnets, let's say this is magnet 1 and this is magnet 2. Magnet 2 experiences force from magnet 1 because of its presence, because of magnet 2's presence in the field of magnet 1. Because we already said, like, you know, every magnet has a magnetic field that runs from its north pole to its south pole, right? So that means like if you bring this guy, the other one, number 2, magnet number 2, towards magnet 1, and then the two magnetic fields will start to interact somehow, right? So therefore what's going to happen is like there will be a repulsion kind of force between those two magnetic fields. So now if you have a current carrying wire, let's say like this, right? If this current carrying wire produces a magnetic field that is surrounding like that, right? Then if you bring in another current carrying wire, right? So just let me use a different kind of color so that we can see. So then this one is going to have also a magnetic field, right? So if you call this current 1 and if you call this current 2, then the red one is going to produce its magnetic field B1 and this one will produce magnetic field B2. If they are close to each other in their proximity, then their magnetic fields will start to interact. You know, like the magnetic field created by wire 1, right, will influence somehow the current carrying wire 2. And like what, you know, and then like, you know, vice versa. It's just like the magnetic field of wire 2 will impact wire 1. Okay, so now what kind of force are you going to experience? So that means depending on the magnetic field, like bar magnets, like current carrying wires also experience a force. Okay, so what kind of force are they going to experience? Will they attract to each other or will they repel each other? So normally, like, you know, if it was in a lab, you know, you could show these things like if the currents are in the same direction, the two wires attract each other. Okay, so that means those two, they are going in the same direction, then automatically like will experience a force between them that's going to be an attractive force. The force over here will attract the force on the other one. If you have two current carrying wires and if the direction of the current is in opposite direction, right, then in this particular case you'll have a magnetic field that is going in this direction in wire 1, and in wire 2 the direction of the magnetic field is going to be like that, like this, right? So in opposite direction. Then the two will start to repel each other, so you will have force from here and then you'll have force from there. And of course the forces are like, you know, the forces are going to be the same, the equal amount of forces, because of action and reaction from Newton's second law. Okay, so probably like you may ask in terms of magnitude how much that force is. So that force can be calculated, you know, the amount of force you will experience in a magnetic field per unit length is equivalent to 2 times k prime I1 I2 divided by the distance between them. Okay, so this is a relationship between the two, like how much is that force. So normally the force is, so F normally represents the force between the two current carrying wires. L is length, the length of the wire. Okay, and then K prime, you know, the textbooks uses K prime, it's some kind of constant, 1 times 10 to the power of -7, and it has a unit equal to Newton per ampere square. Yeah, and R the distance between the two. Okay, distance between them, between the wires. Okay, so this is how you will normally just find the forces between the two of them. Okay, so once again, like we already mentioned, that like the two forces is going to be if you have two parallel current carrying wires, if the currents are moving like this direction, then there will be an attraction force. But if the currents are in opposite direction, then the forces are repulsion. Okay, so just to remind you once again, like the force between them per unit length can be calculated as 2 times k prime, which is a constant for this calculation in most magnetic field related force calculations, divided by r. Okay, length is like, you know, depending on the length of the wire, so you may consider this is your length. Then I1 and I2 are the two currents that you measure in ampere, and R is of course the distance between the two. Okay, so now how about a charge? What if you have a charge moving in a magnetic field? So if you have a charge that is sitting, does it experience a force? Then the answer is no. Okay, if you have a charge and you let that charge flow in a magnetic field or move in a magnetic field, will it experience any kind of force? Then the answer is like, you know, maybe. Okay, so why maybe? Because sometimes the charge can be moving in a magnetic field in a certain direction, and then it might not experience any kind of force. So, but you know, physically, the amount of force that is experienced by a charge moving in a magnetic field. So what it means is, this is a general one, like, you know, if you have a charge, any kind of charge Q that we have been talking about, like in the previous topics, like let's say you have a test charge, positive test charge. You take that positive test charge and then let it move in a magnetic field. Okay, so magnetic field can be in any direction. So let's assume this magnetic field increases to the, the direction of the magnetic field is to the right. So you bring this guy and then let it run inside the magnetic field. Then in some situations it's going to experience a force. Okay, so if this guy just normally flows or runs where there is no any kind of magnetic field, then it's not going to experience any kind of force. Okay, so now in general, how much force does it experience? So let's assume that like you have a magnetic field that is indicated by X. Okay, so every time if you see a magnetic field that is X, it means into the page. That means like that is, so if you are sitting in front of your computer, then the magnetic field is running away from you, you know, or in toward the computer. That's what it into the page means. Okay, so and it's represented by x's. Okay, so you may have also magnetic field represented by dots like this. It's a very common kind of thing, representation. So it means like this is the shows like the magnetic field is coming towards you, towards your direction. So this is also out of the page. Out of the page means like out of the page right now. You see the page that I'm writing on? That means this page. Okay. If it is like coming out and coming towards you, then that direction is known as out of the page. So you bring your Q, let's say your charge, and you let that charge run in this direction. Then automatically, like this positive test charge is going to experience a force, and that means in what direction will that guy move, and that is also dictated by, you know, by right hand rule. You know, that right hand rule is a little different. I don't expect you to know much about it, but just for the sake of making this thing complete, then if you align your fingers mean like except your thumb, in the direction of the motion, or like, you know, this guy has a velocity v in the direction of the motion of the charge, and face your palm in the direction of the magnetic field. Okay, then your thumb will indicate the direction of the force. So in this particular case, like your fingers are flying in the top, right? I mean, 4 of your fingers are up in this direction, and then the face of your palm is like away from you, right? That means into the page. Okay, then the direction of the force is going to be the direction of your thumb, and the direction of your thumb, this particular case, will indicate in this direction, as the way I put it in the arrow. I don't expect you too much of this, like I'm just saying it for the sake of completion. Whereas in this particular case, if you align your fingers, let's say again in this direction, let's say the charge is moving. So we have to consider this as for a positive charge. For the negative charge, it's going to be a different story. Let's stick with one charge only. Then in this particular case, align your fingers up in this direction and look at your palm. That means your palm is just in front of you, because your palm indicates the direction of the magnetic field that is coming towards you. So therefore, your thumb is going to indicate the direction of the force. Then this charge is going to experience a magnetic or electromagnetic force in this direction. So therefore, a charge in a magnetic field, a moving charge, if it's not moving, it's not going to experience any kind of force. So, and then the amount of that magnetic force experienced by the charge is calculated as QV multiplied by B, where Q is charge in coulomb, you know, we keep its unit in SI unit, and V is, you know, velocity of the charge, and B is magnetic field. Okay, and its SI unit has a special name called Tesla. So therefore, if you have QVB, then the amount of force experienced by a moving charge, if the charge is moving in a certain direction, then it's gonna be like that. Okay, but if the charge is moving in the direction of the magnetic field, then pretty much it's not going to experience any kind of force. Okay, so magnetic field in general, like if F is equal to QVB, then magnetic field will be magnetic force divided by the magnitude of the charge multiplied by the motion or the speed of the charge. Okay, makes sense. Okay, so therefore, if you take a current carrying wire, right, and put it in magnetic field, right, then it's going to experience force. So as you can see here in this diagram, okay, in this diagram, this side of the diagram, current carrying means what? A charge moving inside it, right? So if you consider the wire as a pipe, then charges are flowing through it. That's what current means. The flow of charge, right, per unit time. So therefore, if you have a current carrying wire, that means if current is flowing through that wire, and if that wire is exposed to a magnetic field, that's the way you see it here represented by X. X magnetic field means the magnetic field is away from you, right? So therefore, that current carrying wire will experience a force, okay? And that force is calculated as, how do you calculate it? So instead of a single charge, so this formula is for single charge, like just single charge that is in a magnetic field. But on the other hand, like if you have a current carrying wire, the way you see it here, instead of charge, now you are bringing the whole wire, but inside the wire that you have like a long wire, that a stream of charges flowing through it inside, right? So in this particular case, the wire is going to experience some kind of magnetic force, and that force can be calculated as Bill with single L, where B represents what? B represents magnetic field. So B is magnetic field. It's already mentioned here, but see, this magnetic field. And I is the usual representation, current. And L is the length of the wire. Okay. So V stands for velocity of the charge, B stands for the strength of the magnetic field, Q is charge, and the unit of the magnetic field will be calculated in Newton per ampere per meter, also known as Tesla. So therefore, the SI unit of magnetic field is Tesla, and it's represented by uppercase T. So now, simple example that is in your textbook, then that example indicates that if you have a charge with a proton charge and the charge of a proton and charge of an electron, the magnitude is what? 1.6 times 10 to the power of negative 16 coulomb, moves at a speed of 1 times or 5 meters per second, perpendicular to the Earth's magnet. This statement is important. Why? Because if it's moving along the magnetic field, then most likely the charge is not going to experience any force. So what is the magnitude of the magnetic force acting on the proton? So you will just simply apply QVB, right? So you at the way we always do, you list your given parameters and then you apply the force QVB, then you find the answer. Okay. So that's how you will normally find the calculations in. Now, the Faraday's law, electromagnetic induction. So what Faraday said is like something very seemingly very simple, but has a very very high influence in terms of electromagnetism. So the law of electromagnetic induction, it says that like if you have a coil of wire and if you let that coil of wire move inside a magnetic field, as you can see in the diagram, then you can generate electricity. You see, it's so probably based on this simple principle that you can create electricity, isn't it? So the idea is like if you have a magnet, so you know, the magnet has its magnetic field like that. Then now if you take a wire, this copper wire, and if you let it rotate inside between this magnetic field, then what will happen? Then if you try to see using a galvanometer or an ammeter, you'll automatically be able to create current. Okay, so that's what the law of electromagnetic induction says. Or the other way around, if you take a ring of wire, and if you move a bar of magnet into that wire, like inside the ring, then you will start to create electricity. Electricity will start to somehow move inside this ring. So this law is just known as like electromagnetic induction, or you're creating by induction. Okay, so now what drives that current? The current is in the wire. You know, any wire, any conductor. We mentioned this before when we talked about like, you know, conductors and insulators. What happens is like it has what do you call this? It has electrons, free flowing electrons, right? So you can initiate the motion of those electrons by, if you go ahead and then, you know, create some kind of potential. So you can create some kind of electromagnetic induction, and then you can start voltage. If there is voltage, then you are literally, and a conductor, then you will be creating electricity. So how do you calculate that, the amount of voltage that is created? Then, you know, delta phi, a term we call it phi, you know, mostly it's a Greek letter phi. It represents the change in you know, magnetic field induction. Then divide that by time, okay, or the change in magnetic flux actually, divided by time. Then that is what the voltage is like. The definition is here. Voltage is induced in a circuit when there is a change in magnetic flux. If you have a change in magnetic flux, then you divide that by time, then that will be your voltage. So delta phi is changing magnetic flux. Okay. So the voltage EM, sometimes known as electromotive force, induced is proportional to the magnetic flux. Okay. So, you know, sometimes it's represented by, the electromotive force is represented by like a Greek letter epsilon, something that looks like uppercase E. Then equals voltage times delta V. Okay. So then how much voltage is induced? So let's say you have a single wire, you get like a single equation like to calculate how much magnetic flux that you're going to get. But before I go further, how much is this magnetic flux, and then how do you normally like calculate magnetic flux? So the magnetic flux can also be, you know, is equivalent to the strength of the magnetic field multiplied by the area. There is an angle involved, but we're not going to touch that it involves some kind of trigonometric function, but we don't go that further. So here you have like this flux. So phi represents magnetic flux is equal to B times A, where so phi is flux. You know what kind of flux I mean, magnetic flux. This is magnetic field strength, or just simply magnetic field. Then A is the area across which that magnetic field flows. Alright. So now the question is, like, if you try to list your given parameters first, you need to find the flux in the coil. So you have N is the number of turns, B is the magnetic field, and A is the area, right? So if you remember what I said in the previous slide, phi is calculated as B times A. But that only works for one coil. But if you have like n number of coils, then that's going to go to n times B times A. That's NBA. Phi equals n is 50, B is 0.4, and the area of the coil is 0.03 meters squared. Okay, so you know, it can be squared, it can be any kind of, but it says a coil, so therefore some kind of circular thing. Okay, so you multiply that, then the answer is this. Then question B says, what is the induced voltage? So the induced voltage is, you need to find the change. Okay, so the change. So it literally says here the final is 0. The final. What do we mean by the final? You know, we need to find delta phi. Delta phi is phi final minus phi initial. So just symbols, I mean nothing else. Then you already found the final is, you've been told it's 0, and then minus the initial is that much, 0.6 Tesla meter square. That's how. Doesn't have any special name for the flux. Okay, so if you find this delta phi, we already said electromotive force or change in voltage is equal to delta phi divided by time, right? So in how much time did that 0.6 happen, right? So delta V is going to be what? I think 2.4. And the SI unit of voltage or electromotive force, we already discussed this. We talked about Ohm's law in the previous materials, right? So therefore, it has become like that. Okay. I know the textbook uses just simply the positive one. The negative, you know, sometimes that you may come across like, you know, in my calculation, in the previous one, you saw it like delta phi. When you say delta phi, it has to be from the final to the initial and so on and so forth, right? It may have like a certain kind of its own meaning. We're not gonna touch it. It's discussed by some kind of its own law known as Lenz's law, right? It tells you the direction of the current flowing in Michael Faraday's electromagnetic induction. But that's not going to be pretty much as part of this this material, given that like the material isn't really as in depth as in other college physics or university physics. Okay, so this is the end of the chapter in terms of theory, but let's go ahead and then try to solve a few nice examples. All right, so we can start with the very first example. Then I'm going to go ahead and then pick problems directly from the text. They're going to be straightforward and easy. We're going to keep it simple. So starting things like with little by little, and then, you know, if you understand most of this, what is happening in here, what we are discussing in here, then, you know, it's just by the end of the day you'll have like enough material to understand everything, right? So E1 from the textbook, it says 2 bar magnets lying on a table with their south poles facing each other. So as always, we go with our given. Okay, so given, let me use this. So what is given? So you have 2 south poles, so you have 2 bar magnets. They're facing their south poles, and then there's a south pole here, there's another south pole here. And it says like each other, and then they are exerting forces. Now for the force that is equal to 18 Newton. Now the question states like if the distance between the 2 poles is tripled, right? So you may imagine, like as an example, just say the distance between them was 1 centimeter. Now the distance between them is triple. It means now you have the poles and the distance between them is triple. Okay. Then now the distance between them is like, you know, based on our example, it's here, it might not be 3 centimeter, it can be 2 centimeter here, 6 centimeter there, and so on and so forth. But I'm just giving you an example in terms of the numbers. Then now the question is, how much is the force between them? So according to Coulomb, Coulomb's experimental findings, you can say, okay, the magnetic force between two bar magnets is proportional to the inverse square. Square of the distance. The distance between them. Alright. So that means the force between them, alright. So if the distance between them increases, okay, the force decreases. Okay, and then that relationship can be like, even it's a square, it's not only just that's the way it is. So if you use a symbol of proportionation, then that means 1 over r squared. What this shows us, like, so let's say first the force was 18 Newton. When the distance was between them was, you know, you can call that distance x meters, right? Then how much force are you going to get if now the distance is 3x meter? Okay, I don't know how you want to approach the problem, but you can find a proportionation kind of relationship between them. So what happens is, like, in a proportionation, you can do proportional equations. If you have done proportional equations, then you can translate this. So I don't know, when we were in high school, maybe might not be really a direct kind of approach, but whenever we come across a problem like this is how we usually solve it. Like what we say is, like, if it's an inverse relationship that you are having, you can say like you have 18 Newton when the forces, we know that the force relationship is a square, inverse square, so that means 1 over x squared. So now the force that you are trying to find now is like 1 over 3x squared. So the distance tripled. I'm just showing you the calculation, how we get the answers. But other than that, you can just simply say a direct inverse square. You just simply take the amount of force that is given, then you divide it by whatever proportionation the distance is, increases the square. So what we used to do is then we do crisscrossing to find x. Then what will happen is the following. If you do crisscrossing here, that means 18 will be multiplied by 1 over this, whatever, and 1 over x squared is going to be multiplied by this. Then you do the math after that. So that means it's going to be 18 multiplied by 1 over 3x squared will be 1 over 9x squared, right? Is equal to, that proportionation automatically changes to equation. Then this question mark, that means the one that we don't know, multiplied by 1 over x squared. So, x squared cancels out here because you have it on both sides. Why did I use x squared? Because we don't know by how much the original distance was. It could be 1 centimeter between them, then it increased by 3 centimeter, or 3 centimeter between them and it increased to 9 centimeter. But what we know is, like, generally the problem states like it increased 3 times. Okay, it increased 3 times. So then if that is the case, right? If that is the case, then how do you find those things? What's going to happen is then you will end up with 18 divided by 9 is equal to the force that we're looking for. Then 18 divided by 9 is, of course, it's 2 Newton. So this is your answer. So your new force is equal to 2 Newton. All right. More problems. Number 3 from your textbook. Number 3 or number 2? Number 2. There's 2 number 2. Number 2 or E2, the textbook says it E2. 2 long parallel wires. So now it's 2 parallel wires. 2 long parallel wires, each carrying a current 12 ampere. So I1 and I2 equals 12 ampere. Both are carrying 12 ampere. Lie a distance, so the distance between them, represented as R, is 7 centimeter. If you convert this to meter, it will be 0.07. 0.07 meter. Now, what is the magnetic force per unit length? Okay, that means you are asked to define F over L is what? Okay, so the solution is going to start with the choice of your equation, and the equation is F over L is equal to 2k prime I1 I2 divided by R. That's what we said. So your F per length L equals 2 times your K value is 1 times 10 to the power of minus 7 Newton over ampere squared multiplied by 12 ampere multiplied by 12 ampere divided by the distance. You need to convert your distance to SI unit just to get a proper answer. So your ampere, 1 ampere cancels out with another, the other ampere cancels out with the other ampere. Then you'll have force over or per length. You simplify that, most likely you're going to get 4.1 times 10 to the power of -4 Newton per meter. Okay. All right. Then E3 states if the distance between two wires in exercise 2 is doubled, how does the force per unit length change? So given, it says like how the above force changes if the distance is now twice. That means 2 times 7 centimeter. That means your R is now 14 centimeter. 14 centimeter in meter is going to be 0.14 meter, right? You can just go ahead and then apply that same equation, or you try to answer it by looking at the equation. If you look at the equation, the force over length is this formula: 2 times K prime, the constant that we have, I1, I2 divided by R. So force per length for parallel wires, it means like, you have wires and they're carrying current 1 and current 2, right? Then they experience forces. If it is in the same direction, then the forces are attraction, right? Between them. The two forces are equal because of Newton's second law of action and reaction. Now, you can look at this R when R is a denominator here. Force over here is a numerator. So as R increases, F decreases. As R decreases, F increases. And the proportional relationship is not a square one. It's, as you can see, it's just like only over R. So you can answer that like the force, since now the distance is doubled, as you can see here, if the distance doubles, then therefore the force over length is going to be half. Or if numbers are given or the way it's given in this problem, you can go ahead and substitute it, and then you will check the answer by looking at like if it is really half of what we got in problem number 2. Okay, 2 times K is 1 times 10 to the power of -7 Newton per ampere squared. The currents are the same, 12 ampere times 12 ampere. Divide that by R. Now your R is 0.14 meter. Okay. So therefore now your F over L, if you simplify that, you're going to get 2.05 times 10 to the power of -4 Newton per meter. Okay. Look at now what you got here is 2.05. What did you get here? 4.1. You see? So you get half. This value is half of this value. Even without calculating it, you can answer it by looking at like the answer or the value by how much the distance increased. Okay. E4. E4, we find it. E4 states two parallel wires, each carrying a current of 4 ampere. Now again, parallel wires. So you're given parameters carrying each of them. So that means I1 and I2 are equal and they are 4 ampere. Exert a force per unit length. Now the force per unit length is given. And it's found to be 1.88 times 10 to the power of -5 Newton per meter. What's the distance between the wires? Then now you are asked to find R. So your solution, with that your solution will start from the very equation that you already know. The force over length equation is equal to, how's it? 2 times K prime I1 I2 divided by L. Okay, then sorry. Then you are asked to find this R. What you can do is, you can take this to this side and you can take this guy to that side, then you'll just be fine. That means you can do a mathematical elimination if you wish. It's going to be 2K prime I1 I2 divided by F over length. Okay. So then now you go ahead and substitute it. R, K is of course 10 to the power of -7. Keep every SI unit as possible. Everything is in SI units, so you don't need to worry about unit conversion. Then your first force per length is 1.88 times 10 to the power of -5. Then your R is going to be simplified. The rest is just, I'm leaving it for you to plug in it in your calculators. So that is 17 centimeter. Okay. This is what the answer is. Yeah, more problems. Wouldn't hurt. E6, it reads like this. It's going to be not about parallel wires now. It says like a particle with a charge of 0.6 coulomb, means Q is 0.6 coulomb, is moving right angle. See the statement right angle is important? Okay. At right angles to a uniform magnetic field with a strength of 0.5 Tesla. Means your B is now 0.5 Tesla. The velocity of the charge is 800 meters per second. That means V is 800. Now the question is, what is the magnitude of the magnetic force exerted on the particle? It means F is what? Okay. So the solution is going to be pretty straightforward. So a charged particle, as we mentioned it earlier, we'll try to remind you again. If you have a magnetic field like this, that means like into the page, right? I'm just trying to remind you. Into the page. Then if you have a charge that is moving, positive charge Q, okay, and it's moving up like this, then we mentioned that like it's going to experience a force. Okay, in that direction, we already mentioned that. And that force experienced by the charged particle is calculated as QVB, where F is force, Q is charge, column, V is velocity, which is meter per second, 800 meter per second. I want to write it in a better place. So F equals Q, 0.6 coulomb, V is 800 meter per second, and B is Tesla, right, which is 0.5 Tesla. Okay, so if you remember, like, Tesla is what? We said Tesla is Newton per meter, right? So now, you can do a lot of it's not going to be Newton per meter. Tesla is going to be 1 Tesla equals 1 Newton per meter per ampere. That's how it is. Okay, you can do a unit elimination if you wish to, but I can do that for you if you wish to as well. So 0.6, you have a coulomb here. You know that coulomb over second is ampere, right? This is ampere. This is ampere. I took this second to here. I didn't do anything else. So you have 800 meter. Then Tesla by definition is equivalent to Newton meter ampere. Okay. So if you do a unit elimination, this thing eliminates by this, the meter eliminates by that meter, then you will only be left with the force. So if you do a nice calculation, then you're going to get 140 Newton. Okay, so then let's try to move a little and then try to have probably 1 or 2 problems that I have. I mostly prepare the solutions myself first before I solve it here as well. So let's go ahead and then try to solve E7 and E7 and E9. Okay, because pretty much just to make everything full in terms of material coverage. E7 states the following. So E7 a stress segment of wire has a length of 12 centimeter. So you're told the length is 12 centimeter of a given wire, and it's carrying a current of 12 ampere, or it's 7 ampere, and it's oriented in right angles. It's important as well. Tesla equals, B, sorry. Magnetic field, the strength of the magnetic field equals 0.5 Tesla. Your required value, or you're expected to find the force experienced by that wire. Again, I'm going to revise what we have been saying earlier. So if you have a magnetic field, that magnetic field can be between 2 magnets facing in a certain way, or the Earth also has its own magnetic field. Then you have a current carrying wire. So this is your wire, and let's assume that like it's experiencing a current flow of going up. Okay, then this current carrying wire, by applying the right hand rule, like, you know, if you consider this like, you know, your fingers, your four fingers are aligned like that, and your palm is facing away to represent the magnetic field, and your thumb will be like this, right? So the direction of your thumb, this guy, is going to be the direction of the force. That's what I was trying to mention. But this only works for, well, the current direction. The direction of the current is assumed to be the direction of the flow of the positive charge. That's a long story because of convention and other things. Anyway, then you have that force F. Then this force is calculated as, it's already proven to be equal to BIL. Okay. Then your B is the magnetic field, which is 0.5 Tesla. I is 7 ampere, and L is length, which is 0.12 meter, right? In terms of 0.12 meter. You can do unit analysis, as I mentioned it earlier. Tesla means Newton per meter per ampere, right? So if you multiply everything here, then always make sure that like you have your calculator handy. Then, you know, it's gonna be easy. 0.5 times 7 times 0.12 equals 0.42 Newton. Everything is an SI unit, then easy. All right. One last problem, E9. E9 states a coil of wire. Now this is a magnetic induction probe. Coil of wire has how many loops? Says 150 turns. Okay. Has a cross-sectional area 0.03 meters squared. Magnetic field of point B 0.4 Tesla. Now the question is, what is the total magnetic flux passing through the coil? So, you know, you have a coil like this, and you have magnetic field strength flowing through it, right? Then we know that like magnetic flux phi is, for a single coil, it's B times A, magnetic strength times A, but you add N for the number. Okay, so in our case here, our solution is going to be, phi will be calculated as N times B times A. N is 150 turns, A is, or B is 0.4 Tesla, and A is 0.03 meters square. Okay, then do multiplication, like 150 times 0.4 times 0.03, then your flux is approximately 1.8 Tesla meter square. Okay, then that's pretty much it. I hope we have covered everything in electromagnetism. You just simply keep it and then simple, and that's it.